And today we're going to get a glimpse of the first light to shine through that window. Light from other worlds, orbiting stars, far beyond our own.
As one of the most ambitious engineering projects in history, NASA's James Webb Space Telescope is the world's most powerful telescope. Over the past half-century, astronomers have asked a number of fundamental questions about the universe that the James Webb Space Telescope is designed to answer. This ambitious engineering project is estimated to cost $10 billion. For it to achieve its potential, nothing less than rewriting the history of the cosmos and reshaping our place within it. A number of things need to happen just right. Earlier this month, the James Webb Space Telescope, Webb, captured its first color scientific image. In this video, we will show you how the James Webb Space Telescope drastically changed astronomy. Infrared images of the distant universe have never been sharper and deeper than those recorded by NASA's James Webb Space Telescope. It contains thousands of galaxies, including the faintest infrared objects ever seen. In Webb's first deep field, galaxy cluster SMACS 0723. Space has never seen a higher resolution infrared image like this. It is the next great space science observatory after Hubble, creating breakthrough discoveries in all fields of astronomy and answering outstanding questions about the universe. The Hubble telescope allowed us to see further into the universe than we ever had before, but at the time, we had no idea what lay beyond. It was the Hubble Deep Field image of the 90s that was responsible for the discovery of the universe. One of the unique aspects of this experiment was the idea of wasting valuable Hubble time looking at nothing but a tiny patch of sky. The Webb Space Telescope will allow us to look deeper into our origins, beginning with the formation of stars, planets, and galaxies in the early universe. James Webb Space Telescope's first science image was unveiled on July 11, 2022, making history. In comparison to Hubble's similar images of that same patch of sky, Webb's first image shows just how much more detail the camera is capable of capturing. What exactly is this new deep field image showing us? What else does it reveal about the universe? Let's begin by comparing the two telescopes before we see the crisp images this telescope captured. There is a difference between their capabilities. In contrast to common misconceptions, NASA prefers to refer to Webb as its successor rather than a replacement for Hubble. Infrared wavelengths are dominant in Webb's study of the universe, while optical and ultraviolet wavelengths are the focus of Hubble's studies, though some infrared abilities are also present. Essentially, Webb and Hubble work the same way as reflecting telescopes. An oversized primary mirror reflects light onto an even larger secondary mirror, which sends it back to a science instrument through a hole in the primary mirror. In comparison, Hubble's mirror is 2.4 meters wide, or 7.9 feet wide, whereas Webb's segmented honeycomb-shaped mirror measures 6.5 meters wide, or 21.3 feet wide. Currently, Webb holds the record for having the largest mirror flown in space. Using lightweight beryllium and coated with gold, its 18 segments are much more sensitive to infrared light than Hubble, allowing it to see further back into time. Also, the two telescopes are positioned very differently and have very different cooling requirements. While Hubble observes the universe from orbiting Earth, Webb sees it from 1.5 million kilometers away. Lagrange's second point is located here. The gravitational lenses of the galaxies are particularly interesting for astronomers because they distort the light behind them as a result of their gravitational pull. Due to gravitational lensing, Webb can actually see much further away than before. That's why distant objects' light appears curved and warped. According to NASA, Webb detects light more than 13 billion years old, implying that the galaxies in the background formed just a few 100,000 years after the Big Bang. It has taken decades for the James Webb Telescope to achieve its goals, despite many trials and frustrations along the way. We anticipate that these first scientific observations will be the beginning of a new era in astronomy as NASA releases the first scientific observations made by the suite of instruments carried on board the mission. Following the tense launch on Christmas Day, the telescope and its sunshade underwent a series of critical deployments. James Webb would have been a useless disaster if any of these operations had failed. However, the program was executed flawlessly, a process that went more smoothly and successfully than anyone could have expected, let alone hoped. A project of this magnitude can not only be attributed to the skill of the engineers, technicians, and scientists involved. It highlights, too, the crucial role played by the testing of procedures on Earth, which occasionally revealed problems that needed to be rectified before launch. Although this sometimes called schedule slippages and cost increases, it eventually resulted in the perfect telescope. July marked the start of the telescope's operation as the amazing observatory it has long been envisioned as. People who participated in the journey and will work on the data are eagerly awaiting the results. CSA, Canadian Space Agency, and the Space Telescope Science Institute selected the new early release observations as part of a program designed to promote the wide range of science the telescope is capable of addressing. A stunning image of SMACS 0723, which consists of thousands of galaxies, was revealed by US President Joe Biden on July 11th. We can view very faint objects back in time, thanks to the massive groups of galaxies in the foreground which magnify and distort the light of objects behind them. An image shows how the galaxy cluster looked 4.6 billion years ago. Nonetheless, the fainter galaxies in the image, the ones that appear stretched, are at least 13 billion years old, and we already have a great deal of information about them. We will gain a greater understanding of how the first stars and galaxies formed as we see images like these. From the beginning of time, some of these are among the most distant objects known. In the picture, there are a variety of wavelength-related observations combined to create a composite color image. A near-infrared camera, NIRCam, on the telescope captured the image. Additionally, Webb has spotted Stephan's quintet, at least 290 million light-years from Earth in the constellation Pegasus, in which 5 galaxies merge. As shown in the image, a supermassive black hole lies at the center, and stars are formed. By studying the data, we will be able to learn more about the evolution of galaxies and the rate at which supermassive black holes grow. Here's another picture showing the Carina Nebula, one of the biggest and brightest nebulae, clouds of dust and gas where stars are born. It will be possible for James Webb to probe deep inside dust in the infrared light to reveal the inside of the stellar nursery, which we have never seen before, in order to learn more about how stars are formed. It is located approximately 7,600 light-years away in the constellation Carina in the southern hemisphere. Hundreds of completely new stars are visible in the image, as are jets and bubbles that were created by them. Moreover, we are able to see details that are beyond the scope of our understanding. Another spectacular image shows the Southern Ring, or 8-burst nebula, a planetary nebula composed of an expanding cloud of gas surrounding a dying star, or 2 dying stars orbiting each other. Around 2,000 light-years away from Earth, it has a diameter of nearly half a light-year. As seen in the image, the orange foamy shell represents molecular hydrogen, a gas formed by hydrogen atoms bonded together, while the blue center represents an electrically charged gas. We can study stellar death in unprecedented detail in the right-hand image by observing 2 dying stars in the center. Following deployment, the James Webb has undergone months of testing and measurement to be ready to be used as a scientific tool. Initially, each segment of the mirror was focused and aligned. A number of the telescope's scientific instruments, including NIRCam, NIRSpec, and MIRI, have also been turned on and tested. In order to observe deep space sensitively, all these instruments that look at deep space at different wavelengths must be cooled down, along with the telescope. Several months were needed for MIRI to reach the lowest operating temperature, 7 degrees above absolute zero. A telescope's aperture determines the ultimate quality of its images and the details that can be observed. The bigger, the better. In recent years, ground-based telescopes have been constructed with apertures up to 10 meters in diameter. The atmosphere, however, interferes with light reaching the telescope, making it difficult to attain the highest resolution. The telescope's sensitivity is also limited by background light from the night sky, which makes it difficult to see faint targets on Earth. A million miles from Earth and free from the atmosphere, James Webb offers the best, most detailed views of the universe we have ever seen from its 6-meter aperture, making it the largest telescope ever launched into space. In the same way as its predecessor, the Hubble telescope, it will revolutionize our understanding of the cosmos. While the best is yet to come, every new observation, especially at this early stage, reveals a new chapter in a 13.8 billion-year-old cosmic tale. This will forever change the universe. Thank you for watching, and see you in the next video.